In a binary search tree, you are given the root node of a binary search tree, BST, and an integer var. Find the node in the BST that the node's value equals var, and return the subtree rooted with the node. If such a node does not exist, return no. So we're supposed to find the node that equals val. So let's find the node value node in BSD that equals val. Let me copy and paste this to make it quicker. So we're supposed to pass this case over here and also this one to return the subtree retard with the node that does not exist. If it does not exist, return this. So I'll copy and paste this one too. So now let's look into it. So so in this case we're giving the value 2, and we have 2 over here, and we're given the root. So 2, 1, and 3. And we're given the value 5, and there's no matching value for it. There's no node that has the value of 5, so we don't have an output. There's no output. So let's take care of this base case first. So if root is none, return none. Find the node in the BST that equals, so this one will give us none. Find the node in the BST that equals the node's value. So now let's let's find the node. So if the root, the value is equals to val, oops, is equals to val, return node, the root, the subtree. So now let's it should meet all this and return the subtree. That's what the root return will give us. So now let's look at how movement of node of root node. So now let's look at the else if the root.var is less than no, let's make our val, let's put our val this way for better comparison. If our val is less than our root.val, so this is our root. So this is our root for this one, starting from this root. So since we're given 2 here, in the BST, the left child is always smaller than the parent, and the right child is always bigger than the parent node. So now, since our value 2 is smaller than this, that means we have to move to the left child. So return self, let's call on the function itself recursively. So that search the BST. Now let's give it the left child node, the root that left. Let's make it left. So now let's give it val and val. So now we were given a new left child and the value, and now we will check if the value matches the root of val. So now else uh, it will be the same thing as this, except it will be moving to the right. Right. So that's it. Movement to the right. So this, if it's not smaller or not equals to, that means it's going to be bigger. So that means it's going to be bigger. So it will have to move. For example, if we're given 7 as the val, it's not equals to 4. So and it's also not less than this one. So we're not going to get this. So it's going to be bigger. So it's going to move this way. The time and space complexity of this case, time and space complexities are O of H. H being height of recursively solve recursive approach. So since we're going from every child, from choosing from going lower and lower and lower, depending on the value that we have. Um, that's why it's O of H. So H is the height of the thing, and also space complexity is always this is also this O of H, because the deeper we go, the more space they needed. So now let's run it and see if it works. And that's it. It's been able to work well. And that's it for binary search tree. Searching in a binary search tree. This one's an easy one to get to get to get into searching into binary search trees. Let's submit it and see how it works. Yes, and it's been able to work successfully, passing all cases. And that's it.